Okay, students, I want you to all take a piece of paper out. This is your Interim 2 that you took. If you're in school year 2021, you took this in March of 2020. Those are watching it for this year. It focused on proofs and translations, which on the end of the year, the DCAS itself, there's only 2 to 3 proofs, and they aren't as hard as some of these. Some of these aren't bad at all. For example, this first one, even though most of you missed it, you didn't follow what I suggested do with as far as proofs. So I want you to write down these steps on which first thing you do with all proofs when you see on the DCAS is you draw the picture on your own paper. You don't try to visualize it in your head like most of you tried doing probably, and you didn't draw it out, and then you couldn't see what the answer should have been. Okay, so draw the parallelogram out. How do we know it's a parallelogram? Okay, it told us there was a parallelogram. Okay, in the given right here. See right here? That's given. It's a parallelogram. So up top, I just copied off the key information to try to get as much on as scrunched onto a page I could. But up top somewhere it would have told you the given here is parallelogram. So first off, I have no definition of parallelogram. Opposite sides are parallel. So I put that on there. That's the first thing you should have done. What also know is true. So first off, what we're trying to prove now, after doing that, is that the diagonals of a parallelogram bisect each other. So obviously, even though that is one of the characteristics of parallelogram, I can't use that and write that already because that's what we're trying to prove. But therefore, I can go ahead and use the other characteristics of a parallelogram besides the diagonals bisect each other. Well, I have to know what those are, those 4 characteristics off your quadratic hierarchy theorem. Okay, you need to know this because you're guaranteed to have a proof dealing with something with parallelograms, okay, involving it. I told you that's the main thing. So what are the others free underneath the parallelogram? Rectangle, rhombus, and square. You need to know those inside and out and their characteristics. So what else is true? Opposite sides are congruent. And they actually give that to you down here in the proof. Okay, so I should start out with at least that. I also know opposite angles are congruent. Okay, that entire angle would be congruent to that one. This entire angle would be congruent to this one. Okay, now, when I go ahead and look through the proof, they deal with angles here, so I'm going to take those off. Okay, but those are, and then diagonals bisect. Those are your 4 characters that you need to know. Okay, so now let's look at what it's saying here. We're filling this proof in. This angle KJH right here, that angle. We'll even change the color. KJH is going to KGF. Well, I should see that automatically. Before anything else, I should automatically recognize this AIA, alternate interior angles. I told you it's the most popular one when dealing with proofs. You rarely in proofs are going to see corresponding. It's the second most popular is corresponding angles are congruent. And then next would be same side interior angles or supplementary. And lastly, hardly ever in a proof will, I don't know if I've ever seen it hardly ever, alternate exterior angles are congruent. Okay, so you should have got that right away. And then here we have the next one I fill in, KJH. No, KHJ. This one is congruent to KFG. This one, again, alternate interior angles. That's why they have them both in the same step, okay, because their justification is exactly the same, AIA. Okay, well now I should be able to see already right now, which now they've gone ahead, as you see in the next step, written HJ, this side right here, is congruent to FG, which we've already got marked. And of course that is, what's it say? Opposite sides of a parallelogram are congruent, because it's one of the characteristics of a parallelogram. Remember, we were given the parallelogram is true. So then what is that character? Opposite sides of a parallelogram are congruent. So now I should be able to see right away that in this triangle right here, I already have that triangle. I have ASA is congruent to this triangle up here, ASA. Before I even look down at the proof, I should already recognize that. And that's exactly the next step they're saying. Why is it congruent? ASA. Nice and simple. ASA. Should have been very easy. And up here, alternate triangles are congruent. AIA. Remember, I told you they don't write AIA, they write out the whole thing. If two parallel lines are cut by a transversal, that's how it always start. Then AIA, alternate triangles are congruent. Okay, so that should have been easy, that proof right there. All right, next one. A student makes claims about transformations that are applied to a polygon and about the relationship between the congruent and similar figures. So what I want you writing down here are these claims. You don't have to write down the other stuff, okay? You need to know this, okay? You're going to see something like this on the DCAS. This should have been easy. In fact, this was in one of the review packets that I gave you after your last test. And you did this, okay? So what should I recognize about, these are the rules right here. If I have a plus or minus, I know that's a translation, but the problem is it has a negative x out front here. You can't have that with translations. It is straight x plus or minus, one of the two, some number, and comma y, plus or minus, doesn't matter if it's plus or minus, some number. That's all it can be. So once you see that negative there, then they are not congruent. It's nothing, okay? So polygon 1 and 2 are congruent? No. It says justify or refute each. So justify means it's true, and refute means you're saying it's false, and you have to give your reason for it. Okay, so number one is no, it's false because negative x plus 8 does not fit the translation rule order. It has to be x plus 8. Okay, so that's what you can say right there. I'm just verbally telling you. So if you need to pause the video, write that down, write it down. Number two, I see this rule. What do I know this is? You should already know this. We've done this multiple times in assignments. You should know that this is a dilation. How many times? 3 times. 3x and 3y. It's got to be the exact same number. We've gone over this. Class, we did 2x and 2x, or 2x and 2y, for example. It has to be the exact same number. Okay, if it's different, it's not even a dilation. It has to be the exact same number to be a dilation. That's always, this one is always on the DCAS. It may not be like this. It could be a multiple choice and say which one's below, or which one below is a dilation, and you're going to find one that looks just like this, and you'd pick this one. That's what I've seen on the DCAS in the past. Okay. So that's not congruent because that's a dilation. You got 3 times bigger, so false. Also, you'd say that's a dilation of 3 times. Obviously, they're not congruent then. Okay, next one. It says since all congruent polygons are similar, that is true. Remember, all congruent polygons are similar. Congruence falls underneath similarity, but not the reverse way. All similar polygons are always congruent. Don't forget, a dilation is a similar polygon, but obviously a dilation is not congruent unless it was 1x and 1y. Then that dilation is exactly the same. It's congruent then. That's the only way it's congruent, if it's 1x and 1y. If it's any other number at 1 for the coefficient of x and y, it's a dilation. Got to be either bigger or smaller. Okay. Remember, if there were negatives, it can be negatives here as well. All a negative means, remember, it goes through the center of dilation to the other side and makes it 3 times as big. So again, this would be similar to all squares are rectangles, but all rectangles are not squares. Okay, that's a similar idea here. So all 3 of these were false. Okay. Similar polygons can be bigger or smaller, and therefore they are not congruent. Okay, next. Diagram shows quadrilateral QRST with diagonals shown that intersect at point B. Suppose that quadrilateral QRST is a parallelogram. So now we know it's a parallelogram, so all those things are true. What is the correct order of the steps to prove that diagonals of QRST bisect each other? So this time we're actually putting together the steps of that proof from before, because that was also to prove the diagonals bisect each other. So drag and drop. Well, obviously my last step is going to be diagonals R, T, and QS bisect each other. What you're trying to prove is always your last step. So that you can always put in there. Okay. So what do we know is true about diagonal, about parallelograms? You could write them down. Opposite sides parallel, opposite sides, and these are all on your quadratic hierarchy sheet, your four characteristics. That's the definition. Okay. Then you have your four characteristics. Opposite sides congruent, opposite angles congruent, diagonals bisect each other, but we can't use that here because that's what we're trying to prove. But I'm just writing all four characteristics down because you got to have them memorized. So whatever you're trying to prove, you can't use that even if it's one of the characteristics. Okay. Okay, we got opposite sides congruent, opposite angles congruent. Oh, same side interior angles or consecutive angles are supplementary. Remember, same side interior angles or consecutive angles. They like to use consecutive angles oftentimes. So I'm going to be looking at putting these things up here now, since I know it's a parallelogram. So what do we have here? RV is going to VT. RV is going to VT. No, that's going to be the step right before what we're trying to prove. So this is RV going to. These are saying that the diagonals themselves are bisecting, showing that the diagonals themselves are bisecting here by splitting them in half. So that's going to be the one right before. Here we have angle RSQ is going to TQS. Okay, here, notice we have congruent sides and parallel sides. And that's what we have right up here. So this is going to be our step number one right there. No, that's a parallelogram. Here we have the opposite sides congruent. Check. And opposite sides parallel. Opposite sides congruent right here is check, and opposite sides parallel right there. Okay, so that's going to be my first step right there. That's going to number one. I'm not writing them out, I'm just drawing them up there. Okay, so now you go ahead and fill that in. QT and RS are the ones they're using. QT and RS. Opposite sides parallel and congruent. Okay, so now I have that in there. Okay, now what do you have? RS, angle RSQ is congruent to TQS. That one, that one. Okay, why do we have that? From parallel lines cut by transversal, AIA now. Notice we don't have to put the justifications on it. So now this is going to be step two. Now I can prove the triangle is congruent. Okay, and then SRT, I forgot the SRT, SRT. This one is going to be congruent to this. So notice these were the same steps that they had up there on that prior proof. So you could have actually used and helped and use that prior proof. Now you're not going to have this because you're not going to have this many proofs, as I told you on the decast. So you're not going to have two of the same. I've never seen it like this problem right here on the decast at all. When I've seen it with order of the steps, that's actually with constructions, order the steps of a construction. That's the only time I've seen that as far as ordering the steps. So you would have had a proof like the one we had on the prior deal with the proofs. You wouldn't see, I've never seen a proof like this on the decast, but this is just like that one up there above. So you actually could have gone back and found that. Next, we all say that the triangles are congruent. And then I have next for 4 saying that these are congruent, and that justification would be CPCTC if we had to write justifications for step 4. And finally, step 5 is what we're trying to prove. What you're trying to prove is always last. Okay, so you've got this video also not write down, but I would want you to watch this again that week before the decast itself. So you get all this put back in your head. All right, next one. In the figure shown, JS is parallel to GK and HZ is parallel to FT. So whenever I'm thinking parallel lines, as I have here in the given, I should be thinking alternate parallel lines cut by transversal, and I have all the different types of lines, or angles I meant, alternate interior angles are congruent, alternate exterior angles are congruent, corresponding angles are congruent, and same side interior angles are supplementary, or consecutive interior angles are supplementary. Should automatically come to mind. Okay, so now, again, I draw this on my paper. And I go in and I fill in the steps that they have here, just so I can see it on my drawing. Measure angle LQN, that right there, equals the measure of angle LQP, this one, plus WQN. Okay, it's just saying that full angle equals the sum of those two individuals. Okay, that's all it's saying. Remember, for us, that'd be the angle addition postulate, is what that really is breaking it into. Okay, measure of angle LQN plus ZQN, ZQN, so that angle, let's change its color so you see it. That angle plus that angle, this full angle plus that full angle, obviously we see form a what? Linear pair. And they add to 180 degrees. The angles of a linear pair are supplementary. Okay, so that's why you can say that, because they're a linear pair, so therefore they're saying those two angles add to 180. That's correct. Okay, now it says the measure of angle LQP, the smaller one, plus WQN, this other one right here, plus ZQN, this red one right here. So now instead of using the big one and this red one here, they're now, let's change the color so you can see it. So now they want to just say that angle, plus that angle, plus that angle, all three of those also add to 180 by substitution. Remember they said that this big angle equal to two small ones, so now they've substituted that in there. Okay, so that's substitution. Now it's asking us as LQP, and we'll change the color again so you can make sure you see LQP equals WQN. WQ, hold on here. No, I didn't. LQP, LQP. It looks like it says equals WQN. Doesn't that look like it says equals? That's not true. LQP, this small one, does not equal W. I mean a Q. Oh, Q W. Oh, Q. I'm right. I was reading it wrong. QWN. QW. QWN. Oh, right here. QWN. This one right here. Yes. Okay, so this blue one equals that one right there. Why do we know that's true? We got parallel lines cut by transversal alternate interior angles are congruent. Okay, so this angle equals that angle. I just think I can find those angles. Okay, I don't even have to go to the second one. I already know why these two are congruent. AIA. Okay, so that's what I'm looking for. Both of them must be AIA because they're the same ones. So AIA, so that's my answer. That's what I'm looking for. Where do we see that? It's not vertical, cut by result. AIA right there, B. Okay, there's my answer right there. So don't try to jump right to the answer. You need to actually walk through the steps as you just saw me do and actually mark them on the drawing that you've drawn on your own paper. It's way too complicated to try to guess it and try to visualize that all off the top of your head. Okay. Now, in this case, you could have actually got fortunate if you actually just looked right at these two angles. You could have gone right to AIA, but that's not always going to be the case. A lot of times you're going to have to step through and see why those are congruent by going through the prior steps prior to it. So just know that should be your general rule. If you want, you can try it right away. If it doesn't stand out to you right away, then go back, because that would have stood out to me right away. But if it didn't, I would go back and start at number 1 and work my way through and mark everything on it as I go through. Okay, that's a good general rule. You can try to see if you can figure out the answer straight out right away, but if not, go back to number 1, work your way through. All right, part B. A proof is shown with the first statement and reason missing. Okay, what is the missing statement and reason needed in order to prove that angle PLQ is congruent to JLH? So we got to go back up. So let me erase this stuff right here. So we are looking to know that I'm trying to prove that PLQ, so we mark it PLQ, that angle, it's PLQ, is congruent to JLH. JLH. Is that what it was? Did I read right? JLH. Okay. PLQ, let's make sure I got it right. PLQ, yes, is going to JLH. That, oh, dang it. Oh, go back. JLH. Right there. Dang, I gotta make sure. Always double check or triple check as I just had to do there to make sure I did it right. Okay, so ultimately these are vertical angles. We know they're vertical angles. So what I'm trying to ultimately, what they're asking you to do is prove the vertical angle theorem. Okay, so that's what you're trying to prove here. We know it's true by vertical angle, but now we're ultimately proving the vertical angle theorem. So notice it's telling you how they're adding a 180 here. All these. Okay. Now, here's a hint. Notice how they have 2 angles here. I look at the next step down. This next step, step 2, comes as a result of knowing step 1. Okay. And you see here that they substitute in there. So there must have been something that perhaps they both equaled that they were able to substitute in. Well, if I look down here at, here it's only giving me 1 piece. Here it's saying 3 angles add 180. That didn't do me any good. Here it's giving me 2 angles add 180. That's fine, but it's only 1 pair. I need to know both pairs of linear pairs are supplementary, which is what C says right here. So both of these are linear pairs. Okay, add 180, and then I'm substituting in. So then I can take that, substitute, since that equals 180 degrees, I can substitute that right into there, and then I get that angle plus that angle, or not plus, but that angle equals that angle. That's what we see in step 2 through substitution. So this is what had to be given to me in step 1 so that I could use substitution in step 2. All right, there's that one. I've not seen that on the decast before where you're ever filling in step 1, because step 1's always usually given. Okay. And I've never seen you ever have to fill in the given before. It's the first time. All right. I guess I should have checked. I didn't see D over here. One of these two, it's either C or D depending on what they have in step 2. Okay. They both have both pairs adding to 180. So whichever pairs that they substitute in for, that would be it. So if I go look back up here, HLP plus PLQ. HLP plus PLQ, there's that one. Let's make sure the other one is JLH, HLP. JLH, oh, it's not this one. There's no JLH here. So it's not this one at all. Here's my JLH and HLP. So the answer was D right there. Okay, make sure that you look that they have the same 2 angles there. Okay, it came down to those 2, but these are the 2 that they said equal to each other. Okay, through substitution. All right, part C. What's missing from the proof that opposite angles in a parallelogram are congruent? So again, we're given a parallelogram And there we see, remember, definition of parallelogram is opposite sides are parallel, and that's what they're showing right there, given. Okay, and so we're trying to prove that the opposite angles are congruent. So again, you draw the figure. I don't see here, so I would draw it. Just draw and label it. Okay, so L, U, N, Q. Okay, I could have gone L, U, N, Q. Doesn't matter, but I can't skip around. I have to go right in order, one way or the other. So JS. What is missing proof that opposite angles in parallelogram L, U, and Q are congruent? Whoa. So this first proof here looks completely messed up because they don't even have the right letters here in the step one. Here they have the right letters, and here they have the right letters. So they messed up on this. I'm just telling you right here. So we know opposite sides are parallel. That's all it's saying. Okay. So they messed up on writing what it's supposed to be right there. All right, next. Angle QLU. QLU. This angle is congruent to NUS. NUS? What the heck? Do we have a drawing of this somewhere? Okay, so it is the same drawing up here. Okay, so it's the same drawing up here, I'm guessing now. Okay, that's where it's coming from. So this is one of the problems. This is part C, like this is way down the page. So don't forget this, when you have a part A and part B, you got to keep drawing, going down the page to see if you see all the different questions. And this happened to have 3 parts. This went down screen way down the page to get to it. So I need to now, again, redraw this original drawing up here. Okay. So I know that this is a parallelogram because these are parallel and these are parallel. Okay, I'm not going to redraw, but that's what I would do if I was you for the DCAS. Okay, JS is parallel to GK. Okay, so here's my GK right here. That's the same thing as this right here, and JS. That's the same one as that one. Okay, so there's that parallel right there. So there's those 2 parallels right there. Okay, that's the thing. All right, angle QLU is going to NUS. QLU is going to NUS. I mean, sorry, NUS right there. Well, why do we know that? Let's change the color so you can see it easier. Why do we know that this angle is going to this angle? The parallel lines, those are corresponding angles. So that'd be the corresponding angles postulate. Okay. Oh, there it is right there. Then corresponding angles are congruent. And LUN, we have another pair. LUN, go back up. LUN, LUN, let's change the color. Green. LUN is congruent to QNT. QNT, right here. Again, corresponding angles. Same one, and that's why it's in the same box, because they have the exact same answer. Okay, when using the same justification, remember those are called reasons now, then you can put them in the same box as they did there. That's what I do, just to save writing. Okay, so now it says NUS is going to, and you're trying to give the justification for that now. That's what you're trying to figure out. NUS, so let's go to NUS now. NUS, this red one right here, okay, is congruent to UNQ. UNQ. Q. Let's make it red again so we know which ones. Why do we know that this is congruent to this? I should know right away. Parallel lines cut by transversal alternate interior angles are equal or congruent. Okay, so that's my AIA theorem. So I'm just going to write AIA, but you'd write out if two parallel lines are cut by transversal, and there's usually be a drop-down menu you're choosing from. So it's always going to start with that, but so then the pairs of, and we say for this one down here be alternate interior angles. I'm just going to say alternate interior angles. Okay, AIA for that one. Okay. And then don't forget what you're trying to prove is always last. Okay, and they're telling you it's by substitution. What is it we're trying to prove? That the opposite angles of a parallelogram are congruent. So now, since I proved, so this is now, look at it, if A is congruent to B and B is congruent to C, then A is congruent to C by transitive property. Remember that rule? Transitive property I told you to memorize is one of the main justifications in a proof. That's what it is. A, angle A, if you want, I'm just going to simplify down to angle A is congruent to angle B, B is congruent to C, therefore A is congruent to C by transitive property. And that would be my answer right here. Remember what I told you. Transitive property, or if they didn't have that from the drop-down menu, you would choose substitution because they're that close. Transitive property and substitution. You can use either one, and they chose substitution in this case. But if substitution was there, it'd be transitive property. Okay, and so that's what you'd be filling in for that, if right there. Okay, next one. The diagram shows a figure with line QS perpendicular. So I'm going to draw it on my paper again. Now I can put in the perpendicular symbol to RT, and the length of RS is congruent to ST. Well, what should I recognize this now as? If I see this and I see that QS is a perpendicular bisector, I should recognize this situation as a perpendicular bisector. We've talked about this multiple times in class, and therefore this has to be an isosceles triangle, at least, or it could be equilateral because all equilaterals are triangle. Equilateral triangles are also isosceles. So that's going to let me know that I'm going to end up being able to get that triangle QTR is an isosceles triangle. Oh, look it. That's exactly what you're trying to prove right there. Angle QRT is an isosceles triangle. I should have recognized that right away from the given information that they gave me right there. Okay, so we did our given. Again, you mark it. Notice how they didn't mark it for you. You have to mark it. Here, remember I told you that sometimes you put the givens in two separate statements as opposed to all in one. Here you see it separate out. This is actually close. This actually would be a potential DCAS question right here. Okay, this is how it would look actually like this, except for usually you don't ever see two blanks on the same line. It's just one or the other like you see. It's like this, that'd be the only difference. Here they have two blanks. That's usually, I don't think I've hardly ever seen that DCAS. One will be blank and one's filled in. But otherwise, it could look just like this otherwise. Yeah. So now we go ahead and fill in. We just go right on down through. Next it says RS is congruent to ST is congruent. So remember, they just switch it from equals to congruence now. If two things are equal in length, then they are congruent. And that is the definition of congruence. Two things that are equal. Okay, whether their angle measures are equal, then I can still say the angles are congruent. Or in this case, if their lengths are equal, I can say those lengths are now congruent. Those segments are congruent. So we have all that right there. QSR is 90 degrees and QST is 90 degrees. Why do we know that? Definition of perpendicular lines, or just perpendicular. Okay, so there's my perpendicular symbol. Remember I told you that if you see a vocab word in your given, you're going to use that vocab word? Well, that's exactly where that comes into play right there, definition of perpendicular. So now we're able to use and say that those two angles are 90 degrees. Okay. definition of perpendicular. Okay, what do you think is gonna? What do you think? So after you've written down these givens, remember, everything up here really from 1 to 4 is given information, isn't it? Perpendicular is given, so we wrote it as 90 degrees. That's part of the given. This is perpendicular. That's actually given. That's actually given. This is just quickly changing it from equals to congruence by definition congruence. That's all given. What did I tell you to do after you've written down your givens? To identify your what? Your three what? Potential free pieces. What is our free piece here? What is our free piece that we can get on our own? You should recognize it right there. Reflexive property. Okay, so that's what's going right here in step 5. They've already done it for us down here in step 7. So we can't use that there. Okay. So here they have QS is equal to QS reflexive property. I've now marked it in there. Okay. Now you can go, obviously we have these two triangles are congruent by SAS, as you see right there. That's easy. Angle QSR is congruent to QST, definition congruence. Okay, so there they went from the 90 degrees to now that they're equal in measure, now I can say that they're congruent. Okay, so that is that right there. Let's see. So actually from that information, I can already prove those two triangles are congruent. I don't even need a step 5. I have enough information right there to prove these two smaller angles or triangles are congruent. Okay, so let's see from their givens here what they want. Okay, so we have the two segments are congruent. The two angles are congruent. Statement QR is congruent to QT. We can't say that. That's out. So I'm going to go down the order here. Angle QRS is congruent to QTS. I can't make that statement right now. Okay. QS is congruent to MT. QS is congruent to MT. Corresponding parts of congruent triangles are congruent. No, we haven't even proven triangles congruent yet. I don't even know why they're even bringing up this. QS is congruent to MT. We haven't even talked about QS and MT yet at all. So I don't have that. Angle QSR. QSR, yes, is congruent to QST. Okay, that's true. Corresponding parts of congruent triangles. No. Oh, this must be under a difference, not in this 5 through 10 here. When missing statements, measures need to complete step 5. Oh, okay, right here. Oh, it is from all this. Okay, it is. QR is congruent to QT. QR is congruent to QT. Corresponding parts of congruent triangles. No, we haven't proven the triangle is congruent yet. So it can't be that. Corresponding parts of congruent triangles, we haven't proven that yet. Remember, when does corresponding parts of congruent triangles come into play? Notice how these keep using this justification. That can only be used after you prove triangles congruent. Where do they prove the triangles congruent? In step 8. Okay, so I look at all these corresponding parts of congruent triangles congruent, I can wipe them all out because it can't be used till step 9 for that right there. Step 10 then, measure of QSR. Measure of QSR, yes, is equal to the measure of QST. All right, that's it. That is true. So it's G right there. I had to go through all of them to get to the final one. Select all that apply. The only one that applies here happens to be G. Now I've rarely, Well, I guess that would, I don't know why they say that. Oh, and step 9. Oh, dang it. Okay, so that's why. So this one is step 5. Okay, that's why it says select all, because you got 2 steps you're answering for. Okay, so there's step 5. So step 9 now, let's change the color to green for step 9. So that was step 5. Just saying that this angle is congruent to that angle. Now I can say again that the 2 triangles are congruent. And now, remember, I'm trying to prove that's isosceles. So remember, if I'm trying to prove it's isosceles, I need to now show, oops, I thought I changed the color. That side is congruent to that side. So I need to say QT is congruent to QR by CPCTC. So that's what I'm looking for right now. QR is congruent to QT by CPCTC. Corresponding parts of congruent triangles. So there's my other one right there. There's step 9. Okay. So I don't like how they did that because they're trying to throw both steps all in one question. That makes it much more confusing. They should have done here step 5, choose from these, and then go part B, step 9, choose from those. Okay, that would have been much nicer. It's not trying to make it more confusing for yourself. But there's the 2 steps, 5 and 9 right there. Part B, which of the statements could be used to prove triangle QMT? QMT, this triangle right here, is congruent to TSQ, to this triangle right here. Okay, obviously we already have reflection property right down the middle there. They're being congruent. By the H hypotenuse leg theorem. So it's, remember, HL theorem, hypotenuse leg, HL theorem. Where does that occur? Only in right triangles. So we need something to be able to prove the right triangles. Okay, so the first thing I'm thinking that comes to mind, I'm seeing right here, perpendicular for right angles. That's the very first thing, just from knowing that I need to have a right triangle. Let's see if that's going to work then. So MT is perpendicular to MQ. MT is perpendicular to MQ. That puts it right there. There's my right angle I need. That's what I need because that's my hypotenuse, QT, which I have given to me. And now I need one leg, okay, equaling to one of these legs in this triangle. And so what's the second piece they give me? Here, MT equals QS. MT equals that QS right there. Now I have HL, hypotenuse leg, hypotenuse leg. So that is it right there, okay? So you need to know when I have a hypotenuse leg, I need to have a right triangle. So I'm looking for perpendicular somewhere in there so I can get a right angle in there. That's the only one that had that right here. That's why it's a dead giveaway. And then there's your leg that you need right there as well. Okay, next. So there's our proofs done. So now we're into dilations. That's the whole main focus of this. All right, so under dilation, centered at the origin. Remember, that's the key, centered at the origin. Remember, we know under dilations that lines are parallel, so it's going to be y equals 2x. Which of the choices could be the result of a dilation? Well, we just know that the 2x has to stay the same. That y-intercept, in this case b, the -2, can be any number at all. So all we're looking for is slopes being the same. Those two right there. And that's the only ones that have slopes of 2. So that's your free points right there. And that you're going to see on the decals. Just so you know that you could have that almost that same type of problem. All right, so here's actual proof that you have to write out. This would be one, and I think I actually gave you this proof actually on your homework assignment. I believe I did. Okay, so triangle ABC is isosceles. So what's the very first thing? AB is congruent to BC. What do I know? The very first thing I've gone over in class over and over when I have an isosceles triangle, what's my very next step I'm writing in? Base angles are congruent. So after I write down the given, or the first step is the given, all three of these are givens. I have to write down triangle ABC is isosceles. AB is congruent to BC. XA is congruent to YC. So I'm not going to write down those givens. Okay, I'm just gonna write given here, but you write those down in your proof. You can't, there's nothing to draw. You actually have to write those out right there for step one. That's all step one. Step two is what I automatically write down, angle, angle BAC is congruent to angle BCA, isosceles triangle theorem. They're going to understand that because they're reading it. They know what the isosceles triangle theorem says. Everybody knows that. Okay, so you don't have to write it out in words what the whole thing says. You know, right now, long ways to be, if I have an isosceles triangle, then base angles are congruent. Okay, so now I have that. Now remember, I'm trying to prove, remember what we're trying to prove is the very last step, that BXY, the outside big triangle, is also isosceles. So I already have an S in here. Well, since these two right here are congruent, then the two supplementary angles to these are also congruent. Okay. And don't forget, I can use that side with that side, and notice then I would have the triangles congruent SAS, SAS, these two small outside triangles. So the third step is saying that angle BAX is congruent to angle BCY, and uh, 3, that's 2, that's 1, 3. I'm trying to think of the order. I have it written down in your DCAS sheet and your justifications. Congruent come on, let me erase that here. Come on. Are you not going to let me hang that up then? Let's see if it'll erase now. Okay. Isosceles triangle theorem. Congruent supplements theorem. Congruent supplements theorem. Okay. It says if two angles are congruent to the same angles, which are equal in this case, okay, then those other angles are congruent. So congruent supplements theorem. Okay, now I can say that triangle BXA is congruent to triangle BYC. Remember, I got to put it in corresponding order. So I go BXA, I have to go BYC. Okay, always make sure you put it in corresponding order. By SAS. Okay, because I have, if I change it all to blue now, SAS, 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 right there. You should see that. So now I can use CPCTC. So what I need to show is that BX is congruent to BY. So now I can say BX is congruent to BY by CPCTC. And you can just write CPCTC. You don't have to write out the whole thing. Now, so 1, 2, 3, 1, 2, 3. Now I have triangle BXY is isosceles. That's the definition of isosceles when two sides are congruent. So now I can do my last step of my proof. Triangle, and I do it exactly as it says there. Triangle BXY is an isosceles triangle, and that'd be definition of isosceles triangle. Okay, and there's that proof. So write that down. You did this, I believe, in one of your assignments, that proof exactly. And so they have it here. And so you could see that one again, perhaps, who knows, on the DCAS at the end. All right, next. The figure shows point P and triangle JKL. Points JK and P are collinear. Same line, remember, collinear, beginning of the year, first week of school. Same line. Assume the triangle J prime, K prime, L prime is the image. We know it's image because it's got the primes on it. The original does not. Of triangle JKL after a dilation with scale factor of 3/2. 3/2 is 1.5, so it's going to get bigger. That is centered at P. So it's a dilation, got bigger, which means, remember, parallelism is preserved and angle measure is preserved. Okay, those are two key things: parallelism and angle measure, congruent angle measure of corresponding sides. Corresponding angles, sorry. Corresponding angles. Okay, so it says select all apply. So you don't have to draw it, you just have to know what the properties are. So side JK, J prime, K prime is parallel. There's our parallelism. It's got to be the same one. Yes, true. Side KL is parallel to KL. Yes. JL parallel to JL. No side is parallel. It's false. Side JK lies in the same line as side JK. Yes, since these are already collinear, when I go out 1.5, 1.5 of that, it's going to be out to there, 1.5 of that, it's all on the same line. Still collinear. Okay? And it's only on that side only, JK only. Okay, remember? So JK, yes, collinear. Where is that? Yes. Side KL lies on the same line as KL. It's not the same line. No, that's false. JL lies on the same line as JL. Oh, yes, the prime is on the same line. JL. Oh, no, JL. I was thinking, what's the first one here? KL. No, they don't lie on the same line. JL and KL do not lie on the same line. No set of triangle lies on the same line. That's false. There is one side that lies on the same line, and that's of KJ. KJ's lies on the same line. Okay? So there's our all that apply right there. All right, next. The figure shows segment AB and its image. A prime, B prime. We know that's the image. We know that means it's smaller. I mean, that's the image itself. Remember, scale factor is image over pre-image. You just got tested on that. Okay, so you should have known that. You've been quizzing each other with the DCAS sheet. It's on the DCAS sheet as well. So here's my image. Pre-image. Image is bigger than pre-image, so it's an enlargement. It has to be greater than 1. How do I do it? I just look at these signs. 2 divided by 1.5. Remember, that's the same thing as 2 plus 1 is 3/2. Divided by 3/2. I change division to multiplication by the reciprocal. And there's my answer. So scale factor's 4/3. D. That should have been easy. You're going to have one like that on the DCAS. Okay. The coordinate grids show triangle or square FGHJ, which undergo dilation centered at point P. Not the origin this time. The origin is easy because I just multiply the dilation by whatever the coordinates currently are, but that's not the case here because the origin is not the center of dilation. Scale factor of 1/2. So I need to go half the distance. So pay attention on this. This is off of the origin. If it's the origin as my center of dilation, I just multiply each one of these coordinates here by 1/2, and that's my new one. That's easy if it's at the origin. They have now given you, I think in the next 1 or 2, they also are off the origin. So you need to pay attention how to do this because there's a good chance that you will see one of these. Not 3 of these like you see on here, like we've had on here that have come up, 2 or 3 of these, you're only see 1 on the DCAS. All right, so I just take half the distance of each one, and I can either, if it's a straight distance, I just take half. It's easy. So look at 1, 2, 3, 4. It's half of 4. 2. So there's F prime. Now, I don't want to have to calculate that P to G, so I'm going to use the slope formula. Just use slope. Remember, slope is change in Y over change in X. You can do this on every point. Okay, so the slope from P to G, 1, 2, 3, 4, 5, 6 over 2. Okay, now I want a scale factor of 1/2. So I'm going to divide each of these by 2. And now I get 3 over 1. So now instead I'm going to go up 3, 1, 2, 3, and write 1. There's G prime. Okay. If the scale factor was 1/3, I would divide each of the coordinates by 3. If it was 1/4, I'd divide them each by 4. Okay, so I'm going to do the same thing with P to H, or I could look at it. It's 1, 2, 3, 4 diagonals. So now I just go 2 diagonals instead. That's a shortcut way, but I could have gone the slope as I just did there and got to that same point. And lastly, P to J, again, that's 2 diagonals away, so I'm going half that amount, 1 diagonal away. So there's J prime. Okay, so now there is my new square. Right there, it's half the size. Which segment in the prime here will not be parallel to its corresponding segment? Okay, in the original. F G prime. F prime G prime right here. That's a slope of 1. FG, slope of 1. Up 2, right 2. That's also a slope of 1, parallel. And it looks parallel. So that's false. Because that is parallel. So false. Next one. F prime J prime. This one right here. What is this slope? -1. Okay. F prime J prime down 2, right 2. That's -1. So that's false. That's true. G prime H prime. G prime H prime is a slope of -1. Here, down to right to GH, yeah. That's right. That's a slope of -1. J prime H prime. J prime H prime. Slope of 1. And this JH is also a slope of 1. So which segment will not be parallel to its corresponding segment? Unless I'm missing something, all these are parallel. So unless I'm missing like an E or an F that I accidentally forgot to add in there, there is no answer to that. That would be an error problem, unless, like I said, maybe I accidentally didn't copy and paste. There might have been an E and F somehow I didn't get to. That might have been what happened, or else that's a wrong problem. Okay. Let's make this one smaller so we can see the whole thing. So let's go 150. Okay. All right, line segment RS and TU are shown in the coordinate plane, here and here. Line segment RS is dilated by a scale factor of 2/3 with point P. Line segment RS is dilated by a scale factor of 2/3 with point P. Okay, so with point P as the center of dilation to create TW. Okay, so this U is not part of it. Say 2/3, it's got to be smaller. It's got to be somewhere in here. It's got to be smaller. If I was to guess, I'd guess W is right there. That's about 2/3. Well, here, what is this length? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a total of 9. Well, what is 2/3 of 9? 6. So I just go out 6 from T. 1, 2, 3, 4, 5, 6. I was off by 1. That's simple. There's W right there. Okay. Now don't forget to know that. So I could have seen that mine was off if I actually wanted to. Remember I put it. I'll change the color. Remember I put it here for my first guess. Well, remember on any dilations from the center, it has to be lined up. So if I go through there, it goes like that. Notice that doesn't go to P. So that can't be an answer, just so you know. So if I would have done that, I would have seen my answer couldn't have worked. Now, if I do it again through this point, notice it goes right to it. So you could have, without even doing the calculations, if you didn't want to, you could have just lined up S to the center of dilation, and W has to be somewhere along this line. And obviously it's intersecting with this line, so it only puts it right there. So that's another shortcut you could have done to get that. Okay, now again, in doing that, you might need to draw this on a graph paper, plot these points on graph paper, and actually then use a straight edge or ruler to line it up like that. Okay, but you could have done the calculations like I did also and done that. All right, so now select the place on the coordinate plane to plot the point. 1, 2, 3, 4, 5, 6. So what is that point? 7, 3. So that means I need to go down here to 7, 3 and plot the point. Put 7, 3 right there and plot that point. That's what you need to do for that. Okay, line segment BC. We're almost done. Let's see. 2 more after this. Okay. Line segment BC is shown in the XY coordinate plane, B with coordinates 4, 5, and C with 7, 3. The line segment is to be dilated with center A1. A is 3, 1. 3, 1. Right there. Remember, any dilations I can draw, and it has to be along here. So it has to be somewhere along that path. So it has to be somewhere along that path, and I can do it again somewhere along that path. Okay, any dilations have to be along the path right there. So again, I'm drawing that out on paper. If I want to do that, I can see that right there, just so you know. And a scale factor of 1.5. Remember, scale factor of 1.5 means it's getting bigger. It's an enlargement. Don't forget the word enlargement. Sometimes they're going to ask you that vocab word. Enlargement, it gets bigger. So that means B prime is somewhere out here. It's going to be another half of this distance further out. And whatever this is from here, it's going to half this distance further out. Graph points B prime and C prime to create the image of line segment BC in the dilation. To graph a line segment, select 2 points in the coordinate plane. A segment will connect the points. So again, we're going to use slope again. Okay, since it's not an easy counting one here. So slope 1, 2, 3, 4, 5, 6, 7, 8 over 1, 2. 8 over 2. Okay, now I'm going to multiply that by 1.5. Each of these by 1.5 times 1.5 times 1.5. 8 times 1.5 is 12. 8 plus 4 is 12. And 2 times 1.5 is 3. 2 plus 1 is 3. So that means go up 12 from the center dilation and right 3. So that was 8, 9, 10, 11, 12, right 3. 1, 2, 3. Oh, look at it. There it is right there on that extension point right there. And what is that point? 4.5 comma 7. 4.5 comma 7. I do the same thing over here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So I went up 4 and across 8. Again, I'm multiplying by 1.5. 4 times 1.5 is 6, and 8 times 1.5 is 12. Now that's changing y, changing x. So I go up 6. 1, 2, 3, 4, 5, 6, right 12. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, right there. And it has to be right on that line, as we see right there perfectly. So what is that point? 9, comma 4. So I'm going to plot 9, 4. I'm going to plot 4.57. It says it'll connect it for you. Okay, so that's how you need to do it when it is off the origin. Remember, if it was right on the origin of dilation, then I just multiply the coordinates by whatever that scale factor is, and that's my new coordinates. But when it's not, then I need to use slope formula, that unless I can easily count it myself personally. Okay, line segment AB is shown in the XY coordinate plane with A, -2, 0, and 1, 9. Right there is B. The segment will be dilated with center at 7, 0. and a scale factor of 1/3. So obviously it's getting smaller by 1/3. It's going to be 3 times smaller. Remember, if I want, I can go ahead and draw from the center of dilation to that, and I can just stop right there because I know it's coming in closer to it. It's got to land along that way. It's got to land on those 2 segments right there somewhere. I'm going 1/3 of the distance. Well, here's an easy one to count. This is a horizontal distance. Let's count how far from 7 to -2. That's a total of 9. And I'm doing 1/3 of that. What's 1/3 of 9? 3. So I go 3 out. 1, 2, 3. There's a prime. Okay, now this is not an easy count necessarily, so I'm going to go ahead and just use slope. 1, 2, 3, 4, 5, 6, 7, 8, 9 is my vertical distance, and 1, 2, 3, 4, 5, 6 is my horizontal. Notice how they're going to each divide by 3 nicely. So 1/3 of 9 is 3, 1/3 of 6 is 2. So I'm going up 3, left 2. 1, 2, 3, left 2, right on that segment right there. There's my B prime. Okay, and it says, what will be the y coordinate of B prime? What's that y coordinate right there? There's the y coordinate, 3. Make sure I answer that question correctly. So technically, I didn't even have to do A prime because I didn't even bother to read the question. I went and found both of them for you. So therefore, I wasted some extra time, but at least I showed you how to do it if they were asked for A as well. Okay, you really could have just gone right to the B one and done that. All right, last one, I think, right here. Last one. Yes. The endpoints of the segment shown in the coordinate plane have integer coordinates. It's already telling you integer coordinates, no decimals. Okay. Which statement is true? Okay, well, first off, if we want to find the center of dilation, we know it has to be along where these intersect. So I just draw this out, it has to be along there. And then going through these 2 corresponding ones, it has to be right there, along there. And so where they intersect. Oh, where do they intersect? Right there at the origin. So now this can be somewhat easier because it's right at the origin, calculations wise. That's how you find your center of dilation. It says which statement is true? Select all that apply. That's interesting. They say statement, which is 1, and they say select all apply. They should have statement in parentheses S if they want to have more than 1. Okay, segment ST is the image of PQ under dilation with a scale factor of 2. Well, it can't be 2. ST is smaller, so that's got to be between 0 and 1. That's gone. Segment QR is the image of PQ. Wait a second. Segment QR. Okay, we have another one right there. Is the image of segment PQ. That one right there under dilation with scale factor of 3, centered at P. Okay, so if that's my center, how far is it from there to there? That's 2. So it's PR 6. If PR is 6, that would be a scale factor of 3. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that means this is 6 right there. And so from 2 to 8 is a scale factor of 4 times, not 3 times. Or you have to do the whole distance, PR. So that's false. I'll bet you people would pick that to be true because they're seeing 2 to 6 and they're seeing 3 times. They forgot to add the 2 plus the 6 together to get 8. Segment ST, so let me erase this. Segment ST, this one right here, is the image of segment PR. That's the one we had checked. Under dilation, scale factor of 1/2, centered at the origin. So the center of the origin we already know is correct. We did that. Now let's see if ST's distance or length is half of PR's. 1, 2, 3, 4. Yes, and that was 8 as we saw there. So yes, the scale factor is 1/2, center of the origin. So that was crossed out. That's a no. That's a no. Yes for C. So we got 1 true so far. Segment QR is the image of ST under dilation with scale factor of 3/2 at the origin. Well, we know it's at the origin, but remember it wasn't 3/2. It was 4 to 8. So that would be a scale factor of 2. Remember, you got to go in order. QR, that's my 8. ST is my 4. 8 divided by 4 is 2. So it's not 3/2, it's 2. So that's gone. Last one, segment PQ. Okay, so PQ right there, length of 2, is the image of PR. PR is 8. Under dilation with scale factor of 1/4. Yes, it is. 2 to 8 is 1/4. Centered at P. Does it say centered at P? Yes, it does. So those two are true right there, C and E. And that ends it right there. Okay, so you might not have got through this in the whole period, depending on when if I had a sub and the sub started at on time, because that's an hour, 10 minutes. So you might have to finish watching it at home, finish taking these notes. You will not have nearly as many questions of these type on the DCAS, because remember the DCAS is going to cover the whole year. This really just covered 2 concepts, dilations / scale factors and proofs the entire time. All right.